All right, good morning, everybody. This is Greg Wadley. I'm with CTC and Associates and Program Manager for ClearRoads. We're here today for the final webinar for the ClearRoads Project 1603, Standards and Guidance for Using Mobile Sensor Technology to Assess Winter Road Conditions. As a reminder, I do have everybody on mute, so if you have any questions or comments, please enter those into the chat box and we'll address those at the end of the webinar. I'll also put a message in the chat box so that you'll, as a reminder to you to do that. I think that's it. So without any further ado, I'm going to turn it over to the research team from SRF, Mark and Kate. So whenever you guys are ready.
All right. Good morning, everyone, and thank you again for taking the time out of your day to sit in on the final presentation for, as Greg mentioned, the standards and guidance for using mobile sensor technology to assess winter road conditions, or as we've been calling it in shorthand for the last year, mobile RWIS. We're going to have both Kate and I present today. My name is Mark Gallagher, and I'm with SRF Consulting, and
I'm Kate Visdis. I'm also with SRF Consulting.
And for reasons known only to the gods at GoToMeeting, for some reason we show up as Vahid Mastah, who must be the last person to have used one of our GoToMeeting accounts here. Nevertheless, when you see Vahid, think Mark and Kate. So let's dive in. Here's what we're going to talk about today. We want to acknowledge everybody that was part of making this project a success, talk a little bit about what we were trying to achieve, what we found when we did a literature search, and then a survey of some of the ClearRoads states. At that point, Kate will jump in and she'll talk about the sensors themselves and what we did to test them, what we found as the results, and then we'll bring it all back together with what we think we can do with developing some standards on how to describe roadway conditions, and then wrap up with a conclusion. So with that, we do want to say thank you to everybody that helped us make this a success, not the least of which is the ClearRoads Project Subcommittee. Thanks to all the folks who provided guidance as we kind of groped our way through developing a methodology and interpreting the results. Thanks to Greg for keeping everybody on track. And I do want to mention also a thank you to the vendors who not only provided the sensors, but really gave us great technical guidance as we went through the process of evaluating. So thanks again to everybody who helped us on this and made this an interesting project with some interesting results. So let's talk about what we were trying to do with this project. There were really two overriding goals. The first one was to examine the accuracy of the sensors themselves, do a technical evaluation in a sort of semi-controlled environment, but most importantly, a head-to-head comparison. They were all looking at the same thing at the same time. And then, in addition to that, look at some of the practical aspects. What is it like to actually use the sensors? And given the different ways that sensors report and categorize data, what can we talk about in terms of standardizing some of that so that data from sensor to sensor and from agency to agency can be comparable as we move into the future? So those were the two big tracks of things we were trying to accomplish during the course of the project. The first thing that we did was try and take a look at some of the research literature out there that people have conducted over the years to talk about mobile condition sensing. The first thing we really notice is that the evaluations and research on this is fairly limited. There are only a few sensors that have been evaluated. Generally, these evaluations are lab studies, and they're not real world. You're not taking them into traffic driving on the roadway, and as a result, you see individual evaluations of how well something reports a pavement temperature, an air temperature, et cetera, et cetera. When we did find field studies, generally they were talking about friction and the relationship to braking distances and things like that. So they would take out one of these big, like Halliday friction wheel things, pull it around, and then compare that to a sensor. but they weren't really doing overall evaluations for the quality of the data that the sensor provided. In the few side-by-side comparisons, you know, a lot of the times they were just looking at one. It wasn't a true side-by-side, and that really made it very difficult to compare between studies. You would have a sensor being exposed to a set of conditions at a point in time, but you wouldn't have multiple sensors in the same condition at the same time. And that makes that comparison really, really difficult. As I mentioned, scope was generally limited in the studies we saw. All parameters that a sensor could report, the things that we list up top, generally one was singled out at a time. And there was no study that looked at everything that we did under this project. That said, for the things that were compared and the research that was done, we did see that things actually showed pretty similar accuracies between sensors. And that gave us the background of what we were looking at and what we were going to have to try to accomplish. And we very quickly came to the realization that what we were doing was somewhat new. The format and scope of this project, well, was something that hadn't really been done before. So the next thing we did was take a look at that literature review and go out to do a survey of the Clear Roads states. Here you can see the folks that responded to the survey. Generally, there was one response per agency in the state, although a few folks we did get two from different agencies. In particular is Ontario, Canada, and Minnesota, because those folks deal with a lot of snow and were more than willing to share what they learned with us. The big results of the survey looked something like this. These were the big takeaways that we found. First of all, there isn't a lot of mobile sensor use out there. We found 18 states that did them one form or another, at least one vehicle equipped with at least one sensor type. But we found 19 states were planning to add these sensors. So although it isn't prevalent, it's definitely growing. And 9 of those states plan to add more than 80 sensors to their fleets in the next 3 years. So clearly there is a trend out there to want to start collecting data in a mobile environment, and that puts the studies like this in the forefront of importance because these are becoming more prevalent. You should know a little bit about how they perform. One of the things I mentioned early on as a goal is to start figuring out how people use these in a practical environment. Aside from how do they perform, what do you actually do with them? And it was interesting. We asked folks, how do you actually attach these to a vehicle? Side mirror was really common, and I'm sure a lot of the folks listening in have seen the little, I think it's road watch sensors and things like that that sort of clamp onto the mirror of a vehicle and give you a pavement and air temperature. But interestingly enough, there were a fair number that used a trailer hitch where it either clamped onto the ball or fit into a trailer hitch receiver. And that's interesting for a couple of reasons. Number one, it kind of illustrates that these sensors are getting used outside of a heavy maintenance vehicle, a dump truck type environment. And number two, the manufacturers are looking to provide a lot of flexibility in terms of what sorts of vehicles you can use these on and how you attach them. The next thing we asked about was, for this list of parameters, how accurate do you really need them to be? Or I guess more to the point, how accurate do you desire them to be? Most folks said 1% to 3% was going to be acceptable for error in the readings. The one interesting outlier is we asked about water film height. And a lot of folks said 1% to 3%, but a lot of people, actually an equal number of people said 5% was going to be acceptable. And that sort of split, I think, is reflected over in this, the big question we asked in the survey is, how important are these various bits of information to you to be able to do the work you need to do? Everybody said pavement temperature was critical. And I think it's fairly obvious why that is. That determines a lot of the behavior of anti-icing chemicals. It determines freeze and things like that on the roadway. So that was a big one. The other parameters out there, everyone said were valuable or important to them, but weren't critical. Things like reporting a surface condition, wet, dry, snow-covered, icy. What is the air temperature? What is the relative humidity? Friction readings, what is the anticipated friction coefficient, and interestingly enough, the dew point, which of course is a function of humidity and temperature. The last thing that's up there is something that isn't used really by anyone, is water film height. And I think that's probably why we see a lower concern for overall accuracy in these parameters for water film height. So that gives us, again, kind of the background. So what are folks really interested in using out of this? Who's using it? How? All that kind of stuff. So let's talk about the actual sensors. These neat little silhouettes on here are all to scale, so they give you a feel for the relative size of the devices out there. There were 4 sensors that we were able to obtain to evaluate. The Luft Marwis unit, the Tekener RCM 411, Vaisala's DSP 310, and the High Sierra IceSight. All of these, except for the Tekener, have a kind of a dedicated mount. They attach to the vehicle one way or another. The Tekener was unique in that it actually provided an adapter to clamp onto the ball on a trailer hitch. So all of them are roughly the same size. All of them, as you can see for the reported parameters, are roughly the same. But how they mount varies quite a bit depending upon which one you're talking about. In terms of the parameters they report, they were all the same, except the Tekener did not report a relative humidity, and the Sierra IceSight did not report a water film height. So that's what we looked at. A quick note, the Vaisala was actually a 2-piece unit. There's a separate device that pointed down at the pavement, which is slightly smaller than what you see here. We did have both pieces mounted on the trailer, but these are far and away the largest chunks. And you can see that here. The test rig is a beautiful example of our handiwork here at SRF. It looks a little bit more kind of rustic than it actually is. As you can see, there's a basic frame which we constructed and cross-braced to make sure that the sensors themselves were stable and didn't vibrate on the trailer itself. We have a large watertight enclosure for the electronics, that big equipment box you see there. At the very front and back, you can see the 2 Vaisala units. There's one at the extreme rear pointing down and a separate unit up at the front also pointing down. And then the Luft Tekener and High Sierra devices in between. We did create these adjustable mounting height devices, and we just called them sleds, but they're really just a 2x4 with some holes in it. But that allowed us to install the sensors at the manufacturer's recommended height all the way around. That's what we maintained for the test. In all cases, we installed at the recommended height, and we used the default calibration for that installation. And that really gets us into what the user sees. All of the sensors provided software for a user interface. You can see that the Luft, Tekener, and Vaisala are all bits of software that ran on Android cell phones. In all cases, for those, they connected wirelessly to the device, either through a built-in Wi-Fi hotspot in the device or through a Bluetooth, serial over Bluetooth connection. All of these bits of software on the cell phone all send data up to a cloud service from which data can be retrieved later. The outlier here is the High Sierra device. It connected wirelessly as well, but to a laptop computer, and then they provided a Java application that allowed you to see in real time what it was doing. There's also a separate little window that popped up that's not shown here that gives you just a readout of temperature and surface state as well. But this is what you use to kind of see the incoming data and perform calibration, things like that. The High Sierra also provided a physical connection if you chose to use it. I think it was just an RS-232 serial that you could use to connect out. So that's the background. That's what we were trying to accomplish, what we found in original research and with the survey respondents, and the devices we were able to obtain and how we actually installed them. All of that, of course, is pretty boring compared to the stuff that's coming up next. Kate is going to talk to us a little bit about how we did the testing for these, and then ultimately what we found for accuracy and interesting bits about the data. Kate?
So thanks, Mark. So starting in a little bit on the testing methodology, we decided to break up the testing into two phases based on the two goals that were set up at the beginning of the project. First was phase one, which was done at the Minroad facility, which is a closed track in Minnesota run by the Minnesota DOT. You can see it in that map there, that kind of loop that you have that has a bunch of different types of pavement and that is closed off to the public. So we were able to drive around on that and stop, get out of the vehicle, take baseline measurements and compare it to what the sensors were reading, which allowed us to hit that first goal, which is to try and determine the accuracy for each of the parameters of the test sensors. The second test was the field testing that we did. And this was in live traffic. We created a route based around our office in the Twin Cities. This is west of Minneapolis, still in the metro area. This was taken on interstate, state, and local roads to get a variety of different conditions and different speeds. It was about 15 miles total in length and gave us a more practical assessment of what these sensors would look like when you took them out into traffic. However, because we're going through live traffic, we don't have a baseline measurement the same way that we did in that closed track because we couldn't get off in the middle of the freeway and stop and park and take some measurements. For both of these tests, we used cameras both on the front mounted dash cam and a camera pointed to the back in the wheel path to see the conditions while we were driving and get a record to compare our data with. So continuing on with the test methodology and those baselines that I mentioned for the phase one testing, we did a total of 6 runs on the Minroads facility. We used 2 Omega equipment pieces shown in the bottom there for the air temperature, relative humidity, and the surface temperature, more of the meteorological data pieces. And we also used a wet comb, which was that little metal piece up there to measure the water film height. The phase 2 baseline was a little bit trickier because, like I said, we couldn't stop in the middle of traffic. We did 20 runs of this. We did have some baseline measurements that we took from Weather Underground, which is a crowdsourced weather site with very high accuracy, and we used that to get baseline for air temperature and relative humidity to compare it to. And we did 20 runs there. Overall, we had over 90,000 data points that were collected during testing, which took place between December of 2017 and April of 2018. It was a great winter for testing and a bad winter for everything else. We had 5 winter storms and a blizzard. During the test runs, we had a range of temperature between -15 and 57 degrees Fahrenheit. We had a total of almost 63 inches of snowfall, and during that time period, we had 26 days below 0 degrees Fahrenheit. We took these testing in a variety of weather conditions to try and get a broad range of what these sensors would look like in a lot of different scenarios. So that brings us to the more interesting pieces, the results of this sensor. So starting off with some of that meteorological data, we can go with air temperature. So these slides are going to be broken up between the phase 1 and phase 2 results. The phase 1 on the Minroad facility was about determining accuracy. So again, if you remember back to that survey, most respondents were thinking that they wanted about a 1 to 3% error. And sometimes that was never met completely by that 1 to 3%, but keeping in mind that we are typically working with very small numbers. If you're talking about 1 to 2 degrees Fahrenheit, that percent error goes way up. So overall, the average percent error when we were comparing it with the baseline was 3.8 to 14.6% error, with the lowest percent error being the Luft device and the highest being the Techner device. However, that translates to about a 1.4 to a 5.5 degree Fahrenheit difference. So overall, although it's a larger percent, the actual degrees may not be as bad as if you were just looking at that percent. Then the phase 2, which is focused on comparing these sensors to each other. This is an example of the data that we took during phase 2 and comparing it. So here's a graph of one of the runs that we took. You can see that there's this beginning of this downslope where all of them are kind of sloping downward, going from like 60 degrees to about 10 degrees. And this is because we had our trucks and our vehicles stored in a garage. And as we took it out, all of the sensors needed a bit of time to adjust to the actual outdoor conditions. Typically that took less than 10 minutes. You can see that about 600 seconds, they all start to balance out towards that baseline, that weather underground temperature. And as you can see, although the beginning is very low accuracy, as it starts to get a little bit outside, they all sort of end up at the same temperature and end up with the same result. So going with the surface temperature, which is, again, another meteorological result, we had similar things to what we found in the air temperature. Again, that desired accuracy was in that 1 to 3% error range, and again, our observed accuracy was much higher than that. Though it only really translates to 2 to 3.8 degrees Fahrenheit difference in error, which is actually, I think, pretty good. The highest accuracy was the Luft device, which was hitting that average of 2 degrees Fahrenheit error. However, when we were testing on the Minroad facility, which had a variety of pavement, Weissla did perform better accuracy on the aggregate and asphalt pavements. The lowest accuracy for this ended up being the High Sierra, with the exception of the Techner on the asphalt. And you can see too from that phase 2 testing in the real world conditions below, there's a little bit more of a difference in this example, but you can see that where there are hills and valleys in this graph, the sensors generally agree with each other. They might be a few seconds off just based on the placement of the sensors on the trailer, but for the most part, they kind of are in agreement even if the magnitude is slightly different. It also has a little bit of an adjustment period as we're coming out of the garage. You've got that higher temperature that then drops down to much more what you would expect. So the last kind of meteorological result was the relative humidity. As Mark mentioned up front, Techner for this study did not have a relative humidity sensor. It was available in an extra package, but it was not made available to us during the time of the testing period, so we're not able to attain it, but you can add it onto the device for an additional price. Again, desired accuracy is still 1 to 3%. We see a much higher testing accuracy percent error in that 9.2 to 15.5% error, with Luft being the lowest percent error and Weissla being the highest percent error. And in that, bringing it back to the units, that's a 6.5 to 8.4% relative humidity, not percent error again. And then again, like the other two meteorological pieces of data, we have an adjustment period before they all kind of even out towards that baseline that we had gotten from the weather underground humidity. This again took about 10 minutes to even out, but this is pretty typical from one of our test runs where they all kind of make their way up to the baseline, and while they might have some differences, they're generally in agreement with one another. So now we get into the results that are a little bit trickier to quantify, starting with the water film height results. As I mentioned in the testing methodology, we used a wet film comb to take this baseline. However, at the Minroad facility, we were having difficulties using it as we're taking a wet comb on very porous conditions. So all of the water would be too deep within the pore, and you're trying to take the wet comb over a flat surface, it's not going to get any readings. So we had to change the methodology a little bit from what we had anticipated, and we ended up taking a piece of plexiglass back to the garage, spraying water on it, using the wet comb to see what that water film height was at, and then comparing it to the sensor data. The IceSight machine did not measure the water film height, but the rest of them did. And this was the value that we saw had the least amount of agencies using and had the more acceptable higher error, that around 5% error. Of course, because we're working with very small numbers, that error is quite high. We're looking at 60 to 373% error, which obviously seems quite alarming when you're looking at it. But considering that average error is 0.12 millimeters to 0.2 millimeters, kind of taking it back to that small numbers does make a lot more sense. VISLA had the smallest percent error, whereas Techner had the highest error. Looking at the graph, you can see much more of a difference in magnitude than we saw with the meteorological data, which makes sense because, you know, we're using lasers to try and determine how high water is, which is a pretty difficult task. However, you can see that, like the other sensors, it still has those sort of agreements in those dips and valleys, even though the magnitude is quite different. And this you can see especially in this graph, where we have most of them reading at very low or no water film height, but then we would reach a puddle, and these are screenshots from our dash cam that we pulled that match up to those times. Whenever you would hit a puddle or a patch of ice or something like that, all of the data would spike up, obviously, to varying degrees. You can see the VISLA is reading a lot higher on that second graph, but they're all recognizing that there is a puddle there and that there is that water presence there. So another more difficult option to try and quantify was surface state. And this is very difficult just because descriptions of the surface state are going to be subjective. Wet, dry, damp, ice, snow, these all mean different things to different observers, especially when you're talking about, for example, the difference between damp and wet and damp and dry. The amount of water on a roadway that carries it over one threshold is something that's going to be varied from person to person and agency and agency. So we monitored these states by video runs, and when we were taking the Min-Road facility, we would go out and make a physical assessment with, you know, touching the pavement, getting a good look at it. However, you know, it's still going to be a personal decision. So our staff assigned a condition to each of these testing facilities and classified it periodically when we were on the Min-Road facility, and then compared that to the observed state from the sensors and the reported state. So obviously it's not going to be as concrete in terms of accuracy, but we were still able to find some interesting results. So here are some pictures that we had from the Min-Road facility of examples that we would take when we were going out and looking at these conditions. So the first was a snowy condition, and we found that basically whenever there was snow on the road, all of the sensors recognized that it would snow and would report it as snow, or depending on how the sensor classified it, it might say snow/ice. And they were all pretty accurate on that. However, when you get into those damp or dry or wet areas, you have a little bit more of a complicated response. So looking at the March 6th pieces, we had one area that you can see we classified as damp, but the sensors for the most part would read it as wet. However, when you're looking at that second one where we had it as damp, the sensors read across the board a mix of dry, wet, and damp, really just depending on the concrete and, or the concrete versus, you know, other types of pavement, and it really was kind of a mixed bag. However, the nice thing about these sensors is that they are all adjustable in some way or another. The VISLA and the IceSight allow you to go in and manually adjust the amount of water that it'll classify roadways as damp versus wet and damp versus dry. So if you choose to, you can go in and manually change that. And Techner and Luft can't adjust directly, but there are ways that you can make them more or less sensitive, especially if you choose to recalibrate it from the factory sensors. So going based off of our conditions and our assessment, we compared those results to the 29 samples that we took and found that out of all of them, VISLA had the highest number of correct readings. The lowest was the Luft, and the other two were tied or pretty close together, with the High Sierra having 20 correct results and Techner having 21. So last parameter that we ended up measuring, and probably the most difficult to quantify, was friction. Unfortunately for this testing, we did not have a baseline. There is not a good way to take friction measurements without some form of intrusive friction reading, and we were not able to obtain that for this reading. So all in all, it ended up being based on comparing the phase 2 results to one another and seeing kind of how sensors looked across overall. Again, you can see that while the values are different, these dips and valleys come at around the same time. And like the water film height, those would typically be when you would hit a patch of ice or a puddle, and they would all assess a drastic shift in down of friction. Again, going back to that literature review, a lot of the field tests were studying the braking and the friction, and they found that overall sensors had similar accuracy for friction, although again, it's a little bit more difficult to compare to one another. So summarizing these results from the phase 1 pieces, we found that typically sensors performed similarly even if the percent error looked very drastic. Air temperature, we only had a difference of about 4 degrees total from the highest average percent error, or highest error, to the lowest average error, and surface temperature was even closer with less than a 2-degree difference. Relative humidity, again, only about 2% difference, and water film height, again, only about 0.08 millimeters difference, which is quite small. Surface state was a little bit more drastic, but again, we have a little bit harder time quantifying that as it's more subjective, a range of 5 out of 29 results incorrect to 10 out of 29 results incorrect. Like we said earlier, friction is not able to kind of compare to a baseline for this project, so we don't know exactly where we line up, though we did find that results generally were similar across the board. I'm going to hand this back to Mark, who's going to get a little bit more into the conclusions of this study and this project and give us a little bit more depth.
Thanks, Kate. And I see we have a few questions coming in on the bottom that we will get to later on. I'm sure there'll be some good discussion there. So with all that testing, what does it mean? What we had hoped was that in one way or another, we would be able to come out with an overall rank of the sensors. Brand X is best, brand Y is least good, and you can make your decisions accordingly. What we saw and what Kate just described, the data doesn't really support that sort of an overall conclusion. What we did see is that different manufacturers perform better or worse on different parameters that they're trying to measure. And so you can see at the top, Vaisala, for what you might call the non-intrusive detections. What does the surface state look like? What is water film height? In other words, what are you trying to judge by not actually touching it? They seem to do best on those sorts of things. The other end of the scale at the bottom is the Luft sensor. And for what Kate referred to as the meteorological elements, in other words, all of the things that for air, surface, relative humidity, sort of coming in contact with what you're measuring, Luft seems to do the best on those, with High Sierra and Techner falling somewhere in between, neither best nor, in general at least, worse on most things. The important thing to remember, though, is, like Kate said, the difference between number 1 and number 4 on any of these in terms of an absolute value tended to be pretty small. And since there isn't a clear number 1 sensor, if you're looking at deploying these, really it comes down to deciding what is most important for you to measure and then selecting the sensor that does the best job of that, or trying to find the one that has the best mix of accuracy for a given budget that you're trying to meet with these. The other caveat, and something we did not explore with this, since we just had the one rig to mount and test to, is whether or not different installations could produce different results. That's possible, but given that all the sensors provide a recalibration procedure for different mounting locations, the gut feeling is that that would not change this picture greatly. If you mounted differently and recalibrated all of them to that new mounting, we're thinking you would probably see something similar to this. And that's also borne out by the literature search. The testing we were able to uncover also provided results that were similar, not only to each other, but to what we are seeing here. So that is kind of the takeaway from the testing results, is different sensors perform differently, but they all perform similarly. So the next big goal was talking about developing standards for how some of these things, oops, my mouse is doing strange things here. There we go. Developing standards for how you describe these conditions. And as soon as we began looking at the documentation from the manufacturer, we noticed a few things. Number one, as Kate mentioned earlier, there's a lack of well-defined terminology. Where does icy begin and slushy, and where does snow begin and ice, and what is damp versus wet, all of those sorts of things. Those aren't well-defined terms. We also find that when we look at the schemes that have been developed by various agencies out there, everybody's got a little bit different take on how to describe these things and what the underlying measurements to support those descriptions look like. And we found that made it very difficult to translate data, in other words, the numbers that these devices generate, to use that to describe what the road condition is. And so our goal here was to define a limited set of surface states so that a word meant something. Then to try and define the relationship between a parameter like friction and that state. And then lastly, moving on from this, the ultimate goal would be for ClearRoads to present some recommendations to manufacturers and say that for a given condition, it should look like this and it should report a friction like this. And that ultimately would allow for better data portability between different sensors, and also to be able to compare from agency to agency. We found surface classifications. In some cases, there were 7 or more different surface states that were being described. We had a hard time finding some of them to be completely meaningful, and so we tried to simplify it into things that everybody would immediately recognize. And that's what you see in front of you. We decided that for describing winter conditions, these 4 states made sense. Actual frozen water, ice on the roadway, a snow-covered roadway, a wet roadway, or a dry roadway. And we think from a traveler information standpoint, those classifications make sense too. They're simple, and those words mean something to the general public. In terms of defining what those are, ice means that you've got frozen water, in other words, ice, on the roadway surface with 0.5 millimeter or greater thickness. Your friction coefficient that would correspond to that would be something about 0.2 or less. And that means for the public, those are poor driving conditions. When you move to snow, you'd have at least 5 millimeters of accumulated and unplowed snow on the roadway. So it's actually coated and obscuring the surface. Corresponding frictions would be from the top level of ice, something around 0.2 to about a 0.6, which corresponds to what we observed when we were actually out taking the trailer through the real world roadway tests. Again, these represent poor road driving conditions. Things start to improve for travelers then when you get to a wet condition, where you don't have standing ponds of water on the roadway, but you've got a water film thickness of at least 0.5 millimeter on there, and you've got frictions that correspond between about 0.6 and 0.8. And again, that's roughly what we saw when we looked at the data from the units. And this, of course, presents a medium to fair driving condition. There's no special precaution you'd expect people to take in doing that. And then the last one is just dry. Pavement has had a chance to dry out. It's been not exposed to water for 24 hours. your friction is 0.8 or higher, and these are good driving conditions. So we think that this simplified taxonomy makes sense, both in terms of trying to match some piece of measured data to the description and in terms of describing that roadway to people. We're coming down to it. So the overall conclusions, the takeaways from what we saw in the testing. As we mentioned, this is something a little unique. There are very few side-by-side comparisons of these sensors out there. Getting a more comprehensive handle on relative performance is important because we're seeing sensor use is increasing. There aren't a lot of states with a lot of sensors right now, but the number of states using them is increasing, and the number of sensors deployed by each appears to be increasing too. When we asked, most agencies were looking for a percent error of somewhere between 1% and 3%. No sensors were found to meet this, but at the same time, we don't know what the rationale is for that 1.3% either. It may have just been a standard reaction to how accurate you want any piece of data. There could be something deeper there, but we don't know where that number comes from and whether or not that actually has to be met for data to be useful. The big takeaway, again, from the testing is all the sensors perform in a similar fashion for air surface and humidity. When you get into more variable accuracies is when you get into things where you're not touching it directly to measure it. So things like friction, water film height, and surface condition, you're all basically for those trying to judge what they are by looking at the pavement. And that, I think, is going to limit the accuracy of these over time, just because of the nature of what you're trying to do. Again, in no case did we find a best sensor that was just the best at everything. Different sensors were better or worse in different categories or different parameters, but they all, again, performed similarly across all the categories. In terms of describing the condition of the roadway, we do recommend a simplified taxonomy for reporting that. Get it down to conditions that people are immediately familiar with. What are those surface states? And then we tried to tie that back to some objective measure on the roadway. Those parameters, of course, are something that I think would probably need to be negotiated out with manufacturers and what that makes sense to do. But we think it's possible to get some sort of relationship that is relatively consistent in place. And lastly, when we talk about these standards, one way or another, surface state should relate to surface friction, because that is where both literally and metaphorically the rubber hits the road here. The surface friction is going to really determine a lot of the delta in safety and the resulting crash rates and things like that out on the roadway. So those are the big takeaways and what we learned here, in addition to having piles and piles of numerical data that we'd be happy to share if anybody wants to see them. There's, of course, more detail for all of this included in the final report. And speaking of questions going forward, things like that, you know, feel free to contact me at any time. My phone number is there. My name again is Mark Gallagher. My email address is down at the bottom. I'm happy to field any and all questions we might have. And thanks again to our project champion, Kyle, at the Colorado Department of Transportation as well. And with that, we'll go to questions and comments. And Greg, I will kick it back to you.
Sure, thank you very much. I appreciate that. You guys did a good job. So if anyone has any questions or comments, they can throw into the text or the chat box real quick. That's good. I will note that there was one question that we got from Melissa out of Michigan DOT, and it was answered, sounds like by Eric Mengi, but I thought I would sort of read it out And that is, did you have any issues with the Bluetooth or Wi-Fi disconnecting from the devices? And I assume that was talking about the project, right? Because the answer looks like it's talking about this call. So.
Yeah, I think you may have misunderstood that, but yeah, I'll look to Kate to answer that.
Yeah, so we did have the occasional drop in the connection. The most troublesome was the Vizsla device, which would almost always disconnect at some point during our run, sometimes for a few seconds, sometimes for longer. Others had minor drops, but nothing in comparison. However, the distance between the Vizsla and the phones was the greatest out of all of the sensors, so that might have been an impact. The maximum distance was about 25 feet total.
Okay. Scrolling down here again to see if there's anything more that's come in. Scott from Oregon DOT asked, can the data be integrated into an AVL telematics solution?
The short answer is yes, but how you go about that is going to vary quite a bit depending upon the sensor you have. As I mentioned, I think it was the High Sierra actually provides just a hard connection out of it. You can wire in a 232 connection and onto an onboard mobile data computer or other comm unit. The other ones, you would probably need to make a call against their online API and pull the data sort of from the back end, as it were, because all the little cell interfaces are sending those upstream. Other more custom implementations, we'd have to talk to the manufacturer directly, you know what we were trying to connect to.
All right, since there's no more that have come in, I'm going to go ahead and unmute everybody for one last opportunity to ask any questions, and let me do that now.
Yeah. Hey, Greg, we did see a few questions pop up in the chat.
Okay, and those were mostly personal ones that I saw. Well, go ahead and read off something that you may have seen that for some reason it's not registering here.
Sure. We have one from Scott Lucas that asks whether there was a permanent RWIS station on the Phase 2 course.
So the short answer is yes, there was a permanent station that was located around the interstate piece of the Phase 2 route. We did review that data, but we decided to use the Weather Underground data because the route spanned such a large area, about 15 miles, as I said. And because Weather Underground is a crowdsourced network of weather stations, they have these strict requirements that they ask their users to meet before they can accept that data. And there were multiple of those stations across this section of our Phase 2 route. So we tried to use those, knowing that they were accurate and also would cover more of the area than the MARWIS station or RWIS station.
Okay, and let's see, there's Eric. Scott also asks, for the water film height measurement, could the placement of the device in front of and behind the trailer tire have an effect? That's a really interesting question, and I don't have a definitive answer for that, but I will say that they are also, the ones in front of the trailer tire are also behind the truck tire. So there may be some smoothing of any effect there as well. Also, when we did the Phase 1 tests, we isolated it and we used a smooth non-porous surface, and we still saw considerable variability between the devices there. So again, I can't answer definitively, but I am guessing that the difference in placement along the wheel track, any effect of that would be swamped out by just the inherent variability and the readings we see from the sensors. Let me see if there's another one here.
I see one from John Fleming. Go ahead.
Okay, hang on. We've got another one from Scott, and Scott says, was price figured into the calculation? The short answer is no, we didn't. We strictly looked at the performance of the unit here. What do we know about pricing?
We got an estimate from all of the vendors. All of them were within a range between $4,000 for each sensor and $10,000 for each sensor. That might be a little bit different because this project started a long time ago. We have new models that have come out, especially the VISA, which no longer offers the model that we used in our testing, but created a whole new version. But typically, yeah, between that $4,000 and $10,000 range. Whether or not that is worth the increases or decreases in accuracy is up to each agency looking to buy it.
Let's see, and then Greg, I believe you may have seen this as well with Jonathan Fleming asking, is it too late to add the information on the Wi-Fi loss of connection to the presentation? Well, to the presentation itself, yeah, probably. But we do supply materials to ClearRoads as a result of this, and we can put that in there. Is that also in the final report? And in the final report document, we also have that information in there.
Goes in a little bit more in depth about the connections in general as well.
Okay, that's good. And obviously we couldn't do anything about it at this point on the webinar, but you did supply me with a slide deck that you guys used for this presentation. Is it possible to add one slide in there in case they decide to use that for their own purposes? Do you know what I mean?
Yeah. Yep. No. Like I mentioned before, part of the scope of what we have to do is supply materials to ClearRoads, and we can certainly add that information in the version we send.
Okay. Great. Okay. I think that was it. I will unmute all real quick here just to see if there's any other questions or comments. Okay, I think everyone has been unmuted now, so if you have a question or comment for SRF, please go ahead.
Yeah, this is Tom Peters, and I'm curious, do you have a sense for how long these models will be marketed by these various companies? Any kind of turnover, anything you came up with there that you can think of?
It's a good question. We do know that in one case it was, is it Luft? Vizsla,
that has already gotten rid of their old version.
Yeah, Vizsla doesn't offer the version we have here anymore. We don't know, though, how long previous to the test that had been on the market. So it's an interesting question, but in all cases, we just contacted the vendor and asked them to supply a current version of the sensor. We don't know how long that had been available.
Yeah. Yeah, that wasn't expected in your work. I was just curious if you had any information on that, what the turnover is. Okay, thank you.
High Sierra is also currently working on a new version. I don't know when we know that that'll be out, though, or how compatible that'll be with,
Yeah, and they weren't certain whether it was going to be a software update or a hardware update.
Mm-hmm.
Sure. Okay, thank you.
This is Doug McBurn from Montana. Along the lines of the telematics solution, do the softwares that were running these devices provide an API that could be uploaded into another or a program like a travel info program?
It depends a bit on which one you're talking about. The High Sierra, it just provides a COM protocol. So it would be up to the user to take that data and massage that and provide it to whatever external public-facing system that you might want. The other ones, like I said, you can get the data off the back end. There's an API there, and that's how we accumulated the tabular data to work with all this stuff. Whether or not they have something specific that would have nicely massaged and formatted data that you'd port directly into, traveler information or something like that, I don't know. We'd have to check and see.
Hey, Doug, this is Scott Lucas. We have a DTN, and actually we have it ask DTN to port it right into their website.
Okay, Scott, we'll visit next week about that. That's interesting. Thank you.
Yeah, not a problem.
I'll just throw
Right.
one more tidbit. The vendors were all really great to work with, like we said at the beginning, and they all have some way, shape, or form that they can work with you to get that data into whatever system. I mean, they all, you know, when we were first talking to them, explained that, you know, they're working with various DOTs on direct integration into various AVLs and MDSS systems. So I think it's just a matter of reaching out and getting in contact with the vendors to get what you're looking for.
Okay, any other questions or comments? Okay, hearing none. Thank you everybody for your time today. Thank you SRF, and to the TAC members, I will see you next week.